Hi everyone. How can we tell if a polynomial function is even, odd, or neither? I have a bunch of rules in this box here, but let's go straight to some examples. I claim that the function f, where f of x equals 3x to the fourth minus 7x squared plus 1, is an even function. Why? First of all, I like the form of this rule here. Notice that it's a polynomial written in descending powers of x. I don't have any squares of binomials or stuff like that, for example. And bear in mind, I could have a polynomial in x or t or whatever. If you see something like a 0x cubed, you can go ahead and kill it. We want non-zero coefficients. Now, first, I'm going to look at 3x to the fourth minus 7x squared. I think you'll believe me if I tell you that that represents an even function. Take a look at these exponents. A 4 and a 2. These are both even integer exponents. X to the fourth and x to the second represent even functions. Take a look here. Our old friends, y equals x to the second. That's a parabola. Y equals x to the fourth. That's another bowl. Both of these graphs are symmetric about the y-axis. These both represent even functions. And remember, a linear combination of even functions is even. 3 times x to the fourth minus 7 times x to the second. That will also represent an even function. Y equals 3x to the fourth minus 7x squared in green. That's going to represent an even function. Again, we have symmetry about the y-axis. So you should believe that 3x to the fourth minus 7x squared gives an even function. What might creep you out is the plus 1. How do we retain the even property? Well, let's try this out. Y equals 3x to the fourth minus 7x squared. What does the plus 1 do? What does the plus 1 do? It raises the graph by 1 unit. But you see, we still have symmetry about the y-axis. In fact, I could subtract or add any real number. I could add any real number c, put in this slider, and the graph will stay symmetric about the y-axis. We're just sliding this w graph along this y-axis. So you can add any constant to this over here, and you'll still have an even function. If you want to think in terms of exponents, look at it this way. Think of 1 as 1x to the what? 1 is 1x to the 0, because x to the 0 is basically 1 itself. For now, we think of 0 to the 0 as 1. In polynomial theory, we often consider 0 to the 0 to be 1. So if you look at this as 3x to the fourth minus 7x to the second plus 1x to the 0, notice that all the exponents on x are even. We have the nice descending powers form, so it's not a surprise that the corresponding function is even. These even exponents, 4, 2, and 0. It doesn't matter what the coefficients are. I don't care that 3, -7, and 1 are odd integers. That doesn't matter. In fact, when you look at this odd integer 1, actually, because that represents a constant function, remember, all constant functions are even. All constant functions are even. Here's the graph of y equals 3x to the fourth minus 7x squared. What's the graph of y equals 1? It's that flat line, that red flat line, also symmetric about the y-axis. When you add these two guys together, put a plus 1 over here, you still retain the even property. The green graph plus the red graph is the purple graph. You still retain the even property. All constant functions are even, because you can pull this stunt. 1 is 1x to the 0, 2 is 2x to the 0, pi is pi x to the 0, and so forth. That's one reason why we say that non-zero constant terms have degree 0. Non-zero constant terms have degree 0. So a 1, a 2, a 3, a pi, a negative pi, they all have degree 0. 0 itself has no degree. In fact, the 0 function is both even and odd. So this here gives us an even function whether there's a plus 1 or not. In fact, you can add or subtract any real number. Next up, an example of an odd function.